Let me start quickly here with a little comment on the top end about energy security. I think this is on everybody's mind. Important is actually that we demonstrated to the recent situation that energy security is a matter of energy transition, and we have to look a little bit on alternatives for how we can secure our energy supply in the future. And that's what we are doing. We are looking actually for geothermal energy, which is an integral part of the future energy mix. And that comes along with lithium and other critical minerals because these are important for a lot of different verticals in the energy industry, in the emerging industry. And that brings us to the Rio Grande Rift, which is actually an emerging basin in this context. On the bottom, you find a little outline. So my name is Hermann Lebit from Alma Energy, and we're actually exploring for these things, for geothermal energy and lithium as a low-hanging fruit at the moment. So let's go quickly to the Rio Grande Rift. A lot of people are not so familiar with it. Basically, the Rio Grande Rift is an underexplored geothermal province, and it's part of the easternmost lithospheric extension, which is actually manifested in the Great Basin or Basin Ranges area in the United States. Important here is also what the first speaker, Francesco, said about is a mineralization in the area of the Great Basin. And we have a similar kind of mineralization footprint along the Rio Grande Rift, which extended from New Mexico all the way north into Colorado. The rift has a couple of analogs, just in a reference to Germany, the Rhine Valley, the East African Rift, what our last speaker talked about, and of course Iceland, which is a little bit a stretch because it's a rift system on oceanic crust. We are talking here about lithospheric, continental lithospheric extension. Okay. Just give you a little overview what's going on in that area because not a lot of people are familiar with it in terms of plate tectonic setting. As I said, the Rio Grande Rift is basically the last or the easternmost vestige of the Western US or North American extensional system, and it hits basically the Rio extends in the Rocky Mountains, and here are the Great Plains, which is a cratonic part of North America. Driver of the whole system is actually the San Andreas Fault, which is a big major strike slips fault with huge amount of displacement, what you see in the graph down here. On the right, on this side here, I summarized a little bit the deformation history of the area or the tectonic history of the area, which has a couple of implications also for our exploration ideas in the Rio Grande Rift. Important here is basically that you can set up a plate tectonic, let's say kinematic stress system, whatever you want to call it, with some displacements, which are very important because they are fault-forming systems. The San Andreas here is a major strike slip system. The Basin and Ranges extends to the north, northeast, south, southwest. That is the major principal extensional direction. And then here is a secondary strike slip system, which is associated with actually with a proven rotation of the Colorado Plateau, the recent rotation of the Colorado Plateau. Important is also that the Rio Grande Rift is a magmatic rift, so it goes from initial felsic kind of magmatism to volcanism to a mafic rather volcanism, which is actually very nicely demonstrated in the Jemez and the Raton area, which is basically volcanic lineament, which sits here and here. Okay, the McDermott, what was basically partially touched in the first talk, sits here on the border in the Great Basin between Nevada and Oregon, and we come back to that in a moment. But coming back to the Rio Grande Rift, what you see is the Rio Grande Rift is a classical asymmetric rift. It has these huge escarpments or uplifted rift shoulders on the east side. So Sandia Mountain near Albuquerque is a really very spectacular outcrop of that. To the west, the morphology of the system or the isostatic consequences are more subtle. But here we have a lot of magmatic systems. So all the volcanic system or volcanic features are located to the west side. So that's a system, mainly half grabens and volcanic. So it's a volcanic extensional system. So when we look at the subsurface of the Rio Grande Rift, important is maybe this line here. Uh, Coming back, you see this signature here. These are basically volcanoclastic sediments. It's a large formation in the northern part of the rift system, but it's present in other areas. It's not highlighted down here in the Albuquerque basin. Important here is that there's subsurface knowledge is really limited. We had a couple of industry seismic, which is usually not going very deep. It focuses on the cover sequence. But there are some deep seismic like the Rista line, which was, I think, part of the Corco project. We do have some deep seismic and geophysical information, legacy information from the Earthscope project. But important here is you get a mantle upwelling, which is nicely demonstrated under the rift. Um, and it's here done by shear wave analysis of the seismic. But we think there is an asymmetric rift in the sense that we have more um, not a Mackenzie kind of symmetric rift. It's more like Brian Wernick's kind of idea of crustal extension. So that's the situation. Now coming back to geothermal, and our last speaker referred to the potential of geothermal systems in rift basins. So we are basically looking for economic, valuable um, um, geothermal systems here. And this, I like this graph in the middle very much. It tells you a little bit what are the geothermal usages are out there relative to temperature and depth of your reservoir. So everybody knows direct use. This is basically for households and heating and cooling, binary power plants. And then we have here flash steam or hot dry rock reservoirs. That's very important here because we are looking actually in the higher temperature area. The reason is very simple. We can run here flash steam power plants or dry steam power plants as we do already in California, in the Salton Sea, Geyser, Ladarello, and so forth. Important, and this thing is the thermal efficiency. These systems down here, in yellow, have a very low thermal efficiency, which rarely exceeds 20%. Most of these higher temperature systems allow you higher temperature thermal efficiency, which goes above 50% when you run a dry steam system. So that's very important and keep that in mind when you are exploring for these kind of geothermal systems. So here is a little idea what's going on, same graph as before, but what we plotted here is basically the geothermal linear gradient. I know there is a lot of issues about that, but it's just a simplification. And this is the geothermal gradient we actually see on the North American Craton in eastern New Mexico. And this has a lot of data because this is basically a hydrocarbon basin. You may heard about the Permian Basin before, huge oil producer, but fairly low temperature gradient because you cannot heat the oil up too much when it's in the reservoir. Anyway, important here is the other geothermal gradient, which has significantly less data because there's not a lot of well penetration in the rift system, but we see evidence for a very high geothermal gradient. Important here is I show you here three examples. This is number one, number two. And that's quite funny because number one was drilled as an oil wildcat. It hits its objectives at about 12,000 feet of depth, so a little bit more than 3 kilometers. Then they put half of a mile away or 800 meters away, they drilled a second well and they failed before reaching the objective at about the same depth because the well got too hot. So they had a lot of issues, so they had abandoned this drilling exercise after. And the last survey was basically in this temperature range. So that's a clear indication that the area is basically driven by presumably convective heat transfer. And that's very important because when you move a lot of fluid, a hot fluid around. Okay. Then
You're
when
close to
you,
the 10 minutes now.
pardon?
You're close to the 10 minutes now.
Oh, okay. Then I have to go. Okay, good. All right. Then on the convective side, so what we are looking here in the area is basically the fault-related system, and here we're looking for convective systems in the area, And we do a lot of work here. This is remote sensing exercise where we actually try to identify faults, recent faults, and you see they are fitting these system very well. Okay, what we have implemented before, showed before. Okay, coming back to the mineralization, there's a lot of magmatic activity or volcanic activity in the area. We have lava flows. This is a very recent one. We have rhyolites. We have alteration of rhyolites. And at the rift shoulders, at the escarpments, we have actually exposure of spundium ore deposits and labitolite deposits. Okay, so that's very important. But we are looking for aqueous system related to these source rocks of lithium. And you have seen Thakapas. Important here is really that you have these volcanoclastic sediments in the area, and we have that as well in the Rio Grande Rift. And we are looking for this illite-smectite transition where we have high concentration lithium concentration in illites. Coming back to the aqueous system, we try to look in certain wells, abandoned wells like this one I showed before. The problem here is the water column could not be sampled because it's filled with meteoric water. And that's a very important point when you do this sampling. You have to make sure that your fluid is actually representing the formation fluid in the reservoir, and it's not a fluid which is actually diluted or altered by meteoric water. In this case, this is basically presumably infiltration from the higher level aquifers. All right. So we have not a lot of information in that area. So we need to drill a deeper well penetration to test, to check for the lithium and the geothermal potential in that area. So we are pushing for the next thing is to drill a deep well. And as we say in the oil industry, you're never learning until the Kelly is turning. So, but coming back to the system with meteoric water, we do have actually some very interesting aqueous lithium uh, discoveries in the country, and they seem to be associated with extensional systems. Because to be honest with you, everybody heard about the Smackover. The Smackover sits actually in southern Arkansas, northern Texas here, and actually the Smackover is a shallow marine sediment sequence which has an alkaline environment which lithium likes as a reservoir, and the concentrations here are basically in the 200 200 ppm range, as was recently published in a Nature paper by the USGS by Catherine. Okay, but as I said, we are sitting here at the breakaway system of the Gulf of Mexico, or we call it now different, I heard. Anyway, so that is basically very important. And inside this kind of system, we do have another new play, which was actually recently discovered by us, which is not as good as a Smackover, but it's a little bit less in concentration, but we are checking now economic capabilities or economic potential for that system. Has about 6 million tons of lithium carbonate in it, based on a conservative uh, reservoir assessment. So at the end of the day, what it needs for rift systems, we are looking in the Rio Grande Rift. It's a little bit similar to the East African Rift. We do not have yet the breakthrough in terms of lithium concentration in rift systems, but we have all the ingredients, what we heard before in the talks. We have a high temperature aquatic system, geothermal, hydrothermal system, where we expect lithium concentrations in certain alkaline formation environment, which are basically high enough to produce lithium and geothermal energy. Thank you for your time.
Thank you, Hermann. Great talk, great overview. There's time for one or two questions. Just as before, please raise your hand or unmute yourself and ask right away.
Hello.
Yes.
So, great talk. What is the sedimentary infill of the basin? What kind of lithologies you are drilling through?
So what we are drilling through is basically at the top, you have the classical basin fill. This is basically tertiary and upper Cretaceous sediments. This is partially lake sediments.
Lake.
Okay. Lake sediments are in the system, and so we have usually it's clastic. When you go deeper in the system, in the Permian, you have a lot of carbonate, so that's basically the leftover of the cover sequence. So you get the same what you expect there. And then you have actually you drill down into the basement. So you have actually also Paleozoic sediment sequence, which can reach all the way down to the Cambrian. But important for us here is the proximity to volcanic sediments. There is a
Sure,
caldera
sure.
in the area, and I showed you the rhyolite. And
Yeah,
there
yeah.
is
What's the age relationship between
the
the
age of the
volcanism and the
rhyolite. Yes,
sedimentary infill?
the rhyolite is late Paleogene.
Okay,
Okay, or Neogene, so Miocene in age. Okay.
I see. I see.
And there is also what our local people say there is a remaining caldera which is pre-rift, which is associated with it. But the northern part has a huge felsic rhyolite suite, and you get volcanoclastic sediments in the area, and you maybe have lake sediments, but that is basically, you have to explore that by the drill bit. But we see a lot of alterations along the faults. Oh, I forgot to mention there is near Socorro is a magma body which was actually mapped out by seismic. Um, and LiDAR showed recently there is an active uplift. So we have really deep-seating magmatic activity in the area as well. We don't see that necessarily as a conductive heat source. The Earth is an insulator when you calculate it. However, we see along faults, we see convective heat transport. So we will have definitively a mid-crustal magma body, which is inflating at the moment. Yeah. So
Thanks.
it's a
Okay.
very interesting area.
Thanks a lot.